Welcome back to part two of checking when a function is derivable. You cannot understand if you don't listen first to the part one video. Let us continue. Suppose we have a function, a piecewise function, and I want to study derivability at point minus 1 and 2. So let me start at x equal minus 1. But before, since we're going to study the derivative, let me do the derivative of f prime of x. If x less than minus 1, derivative is 2. Between minus 1 and 2, it's 2x. At 2, it's 1 minus 1 over 3 minus x, because derivative of ln u is u prime over u, and 2 is 0. And derivative between 2 and 3, it's 4. Let me start at x equal minus 1. I want to check continuity. We do first of all limit as x tends to minus 1 minus. If we do the limits, we're here. So it will be minus 2 plus 3, which is 1. At minus 1 plus, we are here. So it's minus 1 all squared, it's also 1. And f of minus 1, it's minus 1 all squared, it's also 1. So limit exists and continuous. Because limit exists and continuous, I want to check derivability. So I do f prime of minus 1. I go to derivative function. F prime of minus 1 minus, so it's 2. F prime of minus 1 plus, I'm here. So 2 times minus 1, it's also minus, it's here minus 2. Because left not equal right, 1 is 2, 1 is minus 2. So we say not derivable because they are not equal. So we can say it's a cusp point. Derivative does not exist. However, limit and continuity exist. If I do add 2, let me check continuity. If I do f of 2 minus, it's 2 squared 4. If I do f of 2 plus, it's 8 minus 4 is 4. And f of 2, it is ln 1, which is 0, plus 2, it's 2. So limit exists and continuous. But if you do f prime of 2 minus, 2 times 2, 4. F prime of 2 plus, I'm here, it's also 4, so it's derivable. So limit exists, continuous and derivable. And if you want to check it, let us do it on GeoGebra. It will take some minutes to do it on GeoGebra because I have a piecewise function, and piecewise function will take time to graph, but I'm going to try to let you see why this is the case. Let me put first of all the first function. You have f of x equal 2x plus 3. I have function, the boundary of this function, I put function, I pick another function, which is f. Start value, I want it less than minus 1. Let me put minus 3 till minus 1, it ends. Okay, so let me erase the first one. This is the first part. I have between minus 1 and 2 another function. Let me name it by k of x, which is equal x squared. Here at x squared, I have function. I want it between k. I want it between minus 1, here between minus 1 and 2. Okay, let me erase k. As you can see here, I have a cusp, continuous. Limit exists continuous but not derivable. Let me do the last one. Let me omit equal to 2. I don't need it because it's already continuous. Let me do the last one. I have a of x. Suppose it's, I want to name it function. Sorry, a of x, not capital. A of x equal 4x minus 4. And I want it 4x minus 4 function a of x between from 2, I have it from 2 till 3, 2 till 3. So let me erase a. What can you say? We can see here I have a cusp, so not not derivable, but continuous. However, here limit exists continuous. I don't have a cusp, even it was a piecewise function. So I don't have a cusp. So that's why here, because I don't have a cusp, so at 2 limit exists continuous, not derivable, as we said. Okay, this is a proof using GeoGebra. Let us continue. Here I want to check at 2. First of all, let me do f prime of x. So it's 2x plus 2. If x less than 2, it's 8 bigger or equal to 2. So first of all, you're going to start is to check limit and continuity. If you do limit as x tends to 2 minus, it will be 4 plus 4, 8 minus 1, 7. 2 plus 8, 16 minus 9, it's also 7. And f of 2, I have equal here. So limit exists and continuous. And if you do f of 2 minus, you're going to get 2 times 2, 4 plus 2 is 6. And here you have 8, so not derivable. So I have a cusp. So here I have a cusp. So it's continuous, but not derivable. So let us go to another example. Here I want to check at 2. If I do at 2, 2 minus it's 8 plus 2 is 10. 2 plus it's 8 plus 2, 10. But f of 2 is 6 because limit exists, not continuous. So no need to continue further. So it is not derivable. Another example, if you have this function, I do first of all limit as x tends to 0 minus, it's 0, 0 cubed, and 0 square root 0 at 0 plus, it is 0, and f of 0 here is 0. So limit exists and continuous. I want to check derivability. I do the derivative. Derivative of x cubed is 3x cubed, 3x squared, and derivative of radical x is 1 over 2 radical x. I do now f prime of 0 minus. F prime of 0 minus, you all know 3 times 0 squared, so 0. But if you do f prime of 0 plus, it's 1 over 0. So it's infinity. So here a limit does not exist. So we say it is continuous but not derivable because here left not equal right, and I have infinite. Okay? You can check it on GeoGebra like we did the first one. Let me see if I have enough time to do it on GeoGebra. Yes, I have some time. So let us check on GeoGebra, because you all know I cannot give more than 10 minutes for each one. So I want to put the first one. I have f of x equal x cubed, x power 3. So I want function f between less or equal to 0. Let me take it from -2 enough till 0. So let me erase the first one. I have another function g of x. I have g of x, k of x equal x power half, or square root x, whatever. So I want, as you can see here, what do I have? As you can see here, I have, if you do the tangent here at 0 plus, it's vertical. You can see it's vertical here. Let me put change the color. It's not taking the color. So here, as you can see, it's vertical. Because it's vertical, so it's infinite. But at 0 before, if you do the tangent at 0, it's horizontal. So here it's horizontal and here it's vertical. So this is called limit does not exist because I have two different tangents. So here we say limit exists continuous, but not sorry, here not derivable. So not derivable. So limit exists continuous but not derivable. So the last example for today, find a, b, c so that the function is derivable at x equal to 2. First of all, to be derivable, it must be continuous. And if you do f of 2 minus, you're going to get 4a plus 2 plus 5b must be equal to, at x equal to 2, 4c plus 3 must be equal at x bigger than 2, 2 plus 4 minus a. And since it's derivable, you do the derivative here, 2ax plus 1. I don't care about x equal to 2 because when I want to do the formula, I do it 2 minus 2 plus, I don't take 2. So no need to take this one. Derivative here is 2. Also, if you replace f prime of 2 minus, you're going to get 4a plus 1. F prime of 2 plus, it's 2. So from here, you can get a is 1 over 4. If you replace now a by 1 over 4 here, in this one, I mean, if you replace a by 1 over 4, and here a by 1 over 4, you're going to get b is a 3 over 20. And similarly here, if you equate these two and a is 1 over 4, you're going to get c is a 3 over 16. I hope that you got one derivability about the cusp, when the function is continuous, limit exists, and when it is derivable or not derivable. See you on Monday in school.